In this video, we're going to discuss Le Chatelier's principle, which goes over how different stresses affect the equilibrium position. So for any closed chemical system, the tendency is going to be to move towards a state of equilibrium. Now, Le Chatelier's principle says that when a system at equilibrium is disturbed by a change, so when we say disturbed by a change, that's what I mean when I say a stress. So when a system at equilibrium is disturbed by a change in a property of the system, it adjusts in a way that opposes the change. Another way to say the exact same thing is if a stress is applied to a system at equilibrium, the system changes to relieve that stress. So how the system changes is it can either shift towards the reactants or shifts towards the products. The application of Le Chatelier's principle is a three-step process. So first you're going to have your initial equilibrium state. Then the second step is going to be a shifting non-equilibrium state. So this is when we're going to say, oh, the equilibrium shifts to the reactants or it shifts to the left. Or the alternative would be that the equilibrium can shift to the right, which is the product side. And then step 3 is you have a new equilibrium state. Now, the stresses that are going to shift or cause shifts in equilibriums are the following. So adding or removing reactants or products. So that just involves changing concentrations. You can change pressure, so that's only going to affect gases. Another stress would be changing the volume and changing the temperature. And let's just add for changing volume, that's also going to affect gases. Okay, so as we've talked about, there's two types of shifts. There's a shift to the right. So that means your products or your concentration of your products are going to be increased because the forward reaction is momentarily favored. Okay, so the key word there is that it's momentarily favored. It's not permanently favored. Okay, it's just momentarily favored until the new equilibrium state is achieved. The other shift is going to be the left shift, which means that the concentration of reactants increases because the reverse reaction is momentarily favored. Okay, so a right shift can also be called like shifting towards the product side. A left shift can also be called like being shifted to the reactant side. All right, so let's talk about changes in concentration. So if we add more of a substance, the system is going to shift in order to consume some of this added substance. So therefore, if we add a product, the equilibrium is going to shift to the reactant side. If we add a reactant, then it's going to shift to the product side. Now, if we remove a substance, the system will shift to produce more of the removed substance. So if you remove a product, your equilibrium is going to shift to the product side. If you remove a reactant, you're going to shift to the reactant side, or the equilibrium will shift to the reactant side. So to summarize how concentration changes causes the equilibrium to shift, I'm just going to write a note at the top of this page just because I don't have a lot of space here. So if you add to a system at equilibrium, which I'm going to just shorten to equal, the equilibrium is going to shift away from the stress. Okay, so you could think of it as A for add, A for away. Meanwhile, if we take away from a system at equilibrium, the equilibrium is going to shift towards the stress. So for this one, you could think take away towards. Okay, emphasis on the T in both words there. Okay, so I just need to draw little arrows to connect these two here. All right. So once the equilibrium shifts to minimize the stress that was put on it, after the shift occurs, then it goes back to a new state of equilibrium. However, when we change our concentrations of either our reactants or products, you do need to be aware that your equilibrium constant Kc is unaffected by any changes in concentration. So we've got an example here of an equilibrium. So I'm going to write in my equilibrium arrows here. And we've got some statements to complete. So if the concentration of nitrogen monoxide is increased, the system will shift to the blank. Okay, so let's find nitrogen monoxide. So it's right here. If we increase the amount of nitrogen monoxide, remember, if you add something, the equilibrium shifts away. So we're moving away. So this means that if we increase the concentration of nitrogen monoxide, that's going to cause the system to shift to the left side, or you could also say the reactant side. So just as a heads up, you absolutely do have to be able to know and predict how different stresses are going to cause an equilibrium to shift, or which direction the stress is going to cause an equilibrium to shift. So if the concentration of nitrogen monoxide is increased, the system will shift to the reactant or the left side, both mean the same thing, and the concentration of the products will blank. So if our equilibrium is shifted to the left side, what that means is we're using up the products to create more reactants. So that means that the concentration of the products are going to decrease, And that's because the reverse reaction is temporarily being favored. And as such, the concentration of the reactants are going to increase. Okay. Now, for this next statement, let's say that the concentration of nitrogen dioxide is decreased. So let's find that in this example. So here's nitrogen dioxide, concentration is decreased. So what this means is when you take away, the equilibrium shifts towards. So our equilibrium is shifting to the left to replace that nitrogen dioxide that we removed. So this causes the equilibrium to shift once again to the left side, which is also known as the reactant side. So what's going to happen to the concentration of the products is they are going to decrease, and the concentration of the reactants will increase, and again that's because the reverse reaction is being favored. Next, we're moving on to energy or temperature changes. So if we add heat to the system, it's going to shift to remove that added heat. So which way a system's going to shift really depends on if it's an endothermic reaction or an exothermic reaction. So let's just draw out or write out some templates for some general endo and exothermic reactions. So we're going to say reactant A plus reactant B plus some amount of energy. So remember, endothermic reactions require energy as a reactant in order to proceed. Okay, so that's going to give us product AB. And then for our exothermic example, I'm going to say reactant A plus reactant B, and I'll scooch this over so it's a little bit easy to see. Gives us product AB plus energy. So remember, an exothermic reaction has heat exiting the system. That's why it's a product. Okay, so let's get back to what happens if we add heat to the system. You can kind of think about energy and temperature, adding energy to a system, kind of the same way that we were treating if you increased the concentration of a certain substance. Okay, so if we increase the energy in an endothermic reaction, remember, we're adding to this equilibrium, therefore the equilibrium shifts away. So if we add heat to an endothermic reaction, it's going to shift to favor the products. However, if we add heat in an exothermic reaction, so if we increase the amount of heat, it's going to shift away. So it shifts to favor the reactant side. So again, how your equilibrium shifts completely depends if your reaction is endothermic or exothermic when you have heat as a stress. Now, if you cool the system, it's going to have the opposite effect. So your equilibrium is going to shift so that it produces more heat, or it replaces the lost heat. Okay, so again, I'm going to write out the endo and exothermic reactions just to make this super clear. So the endothermic reaction, which I'm just going to abbreviate to endo, so A plus B plus energy gives us product AB. And then for the exothermic reaction, A plus B gives us product AB and energy. Okay, so for an endothermic reaction, if we're cooling down the system, that means we are removing the heat, or we're taking away the heat. So an equilibrium will shift towards what you're taking away. So that means that if you cool down an endothermic reaction, the reactants will be favored. Meanwhile, for an exothermic reaction, if we decrease, or if we take away heat by cooling down the system, when we take away, the equilibrium shifts towards, so this would favor the product side. Now, when you make temperature changes to an equilibrium, that is going to affect your equilibrium constant. So your equilibrium constant will either increase or decrease depending on whether the products or reactants concentration increase. So we'll get into that a little bit later in this next example here. So we're asked to consider the Haber process. Now, the Haber process is going to be an exothermic reaction. So it's got a negative amount of energy. So because it's an exothermic reaction, that means our energy term is going to be on the product side. So I'm just going to write energy over here. Now, how much energy there is doesn't really matter. What matters is if energy is a reactant or a product. So if the system is heated, so that means we are increasing the amount of energy, then the equilibrium is going to shift away from what we added. So it's going to shift to favor the reactant side, which you could also say it shifts to favor the left side. Either way of saying how the equilibrium shifts, whether you say reactant or left side, it both of them mean the same thing. So because the reactant side is favored, that means the reverse reaction is being favored to decrease the amount of heat that we added to the system. So this means that the concentration of products are going to decrease because that reverse reaction is favored, and the concentration of reactants is going to increase. Now, since changes in temperature results in our equilibrium constant being affected, what's going to happen to our equilibrium constant is it's going to decrease. Now, why is this? So if we go back to a very basic form of an equilibrium law expression, we have Kc is equal to the concentration of products divided by the concentration of reactants. Now, we just said that the concentration of products decreases, whereas the concentration of reactants is going to increase. So you could either compare your equilibrium constant to the products or to the reactants. You'll get the same answer in the end. So if we look at comparing equilibrium constant to the products, Remember in an earlier video that I said the equilibrium constant has a proportional relationship to the concentration of the products. What that means is when concentration of products goes down, equilibrium constant goes down. For the reactants, if you wanted to compare the equilibrium constant to the reactant concentration, that's an inversely proportional relationship. Okay? How you can tell it's an inversely proportional relationship is because one of your values is in the numerator, the other one is in the denominator here when they're on opposite sides of an equal sign. Okay, so what that means with an inversely proportional relationship is whatever happens to one thing, the opposite happens to the other. So since concentration of reactants is increasing, the opposite must happen to the equilibrium constant. So again, that matches up with the equilibrium constant has to decrease. So again, it doesn't matter if you're comparing equilibrium constant to the concentration of the products or the equilibrium constant to the concentration of what's happening with the reactants, you get the same answer in the end. All right, now let's take a look at what happens when the system is cooled. So I'm going to quickly rewrite this reaction out just so I can write on it. And I'm going to include my energy term. Okay, so if the system is cooled, that means we are decreasing the amount of energy. So whenever we're taking away, the equilibrium shifts towards, okay, because the equilibrium is basically saying, oh, I lost something, I have to make it up, okay? So if the system at equilibrium is cooled, it's going to shift to the product side, which you could also say it shifts to the right side. So the concentration of the products is going to increase because the forward reaction is temporarily favored, and that means the concentration of the reactants is going to decrease, again because the forward reaction is being favored. Now, your equilibrium constant, that is going to increase. So why? So let's write out our equilibrium law expression really quick here. Okay, so I'm going to choose to focus on the products just because it's a proportional relationship, which means what happens to one, the exact same thing happens to the other. So we know that our concentration of products is increasing. That means that means that the equilibrium constant is also going to increase. So that's the mathematical explanation as to what is happening to your equilibrium constant. Moving on to volume and pressure changes, keep in mind that that is going to affect gases. So for gaseous systems, changing the volume changes the concentration of every gas in the system. So to predict the effect of changing pressure, you need to see how many moles of gas are on the product side and how many are on the reactant side. Okay, so the reason why volume and pressure are put together as the same stress is because when you change volume, you are also changing the pressure of a system. Okay, and keep in mind that pressure and volume are inversely related. This is something covered in Chemistry 20 in the gases unit. It's called Boyle's Law, and basically it says that pressure and volume, it has an inverse relationship, so what happens to one, the opposite has to happen to the other. So for example, if pressure increases, that's going to cause volume to decrease, or vice versa. If you decrease volume, right, that is going to result in an increase of pressure. Okay, so as pressure goes up, volume goes down, and vice versa. So the vice versa would be that if pressure decreased, that would be a result as an increase of volume of a container. So also remember that we're assuming all of these gases to act like ideal gases, which means that the size of the gas molecule doesn't really matter, and only the spaces between the gas molecules count. So what this means is that because we assume that all gases act like ideal gases, this means that we're also assuming that there are similar volumes of, in this case, if we're looking at like this reaction, the Haber process, we'd also be assuming that the volume of nitrogen, hydrogen, and ammonia are the same, even though they're different masses. One thing that I just wanted to mention before moving on is going back to this point where we're saying to predict the effect of changing pressure, you need to see how many moles of gas are on the product side and how many moles of gas you have on the reactant side. How you figure out how many moles of gases you have on the product and reactant side is you just look at the coefficients in your balanced chemical equation. All right, so if we increase volume, so that would be resulting in decreasing the pressure. So if we increase volume, which would decrease pressure, the system is going to shift towards the side with the most amount of moles. The reason why this happens is because there's an increase in volume, which means there's more space for more moles of gas. That's why the equilibrium shifts towards the side with more moles of gas. So let's write out what I just said. So it shifts towards an increase in moles. Why? Because there's more room. So when you increase volume, that's going to result in a decrease in pressure. The equilibrium will shift towards the side with more moles, and the reason for that is because there's more space for the additional amount of moles of gas. Now, if you decrease the volume, which will result in an increase in pressure, the system's going to shift towards the side with the least amount of moles, because when you decrease the volume, you decrease the amount of space, so you're going to shift to the side with the lesser amount of moles because there's less space. So let's summarize that. So if we decrease volume, you're going to increase pressure, equilibrium will shift towards the side that has less moles, and that is because there's less space for the moles of gas. So because is that B/C, Now, with volume and pressure changes, that is not going to affect the equilibrium constant. Only temperature or energy changes is going to affect your equilibrium constant value. So let's look at the Haber-Bosch process again, which is also just known as the Haber process. So we have this equilibrium with nitrogen gas reacting with hydrogen to produce ammonia gas. And on the left-hand side, we have, if you really wanted a coefficient here, it would be 1 in front of the nitrogen. So we have 1 mole of nitrogen, 3 moles of hydrogen. So in total, that's going to be 4 moles of gas. So let's just write off to the side. We're talking about the total moles of gas on each side here. So then on the product side, we would just have 2 moles of gas. All right, so now that we are aware of how many moles of gas are on the reactant and product side, we can answer the following questions. So if the pressure is increased for this particular system, it will shift to the product side. Now, why is that? It's because when we increase pressure, we decrease volume, which means there's not a whole lot of space for moles of gas. So we're going to shift to the side that has the least amount of moles of gas because there's less space. All right, if the pressure is decreased, so that only happens when you increase the volume, that means the system is going to shift to the reactant side, because when pressure is decreased, volume is increased, so you shift to the side that has more moles of gas because there's more space to accommodate all those extra moles of gas. All right, now can we think of a scenario where there'd be no shift even though pressure and volume are changing? Well, there sure is a situation where that could happen. So the only way that that could happen is if the number of moles, so again, you're thinking about the coefficients, if you have an equal amount of moles of gases on the reactant and product side, even if you change pressure or volume, that will not result in a shift because there's no side that has more or less moles of gas if you have the same amount of moles on the reactant and product side. So we're going to say number of moles. So again, you're focusing on the coefficients. Is equal for the products and reactants. All right, now we're going to talk about adding catalysts or inert gases, and what you need to know is they are not going to cause equilibrium shifts. Now, for catalysts specifically, they allow a system to reach equilibrium faster, but they do not change the equilibrium constant and they do not change equilibrium concentrations. For inert gases are also known as noble gases, and when you add them to an equilibrium mixture, they do not cause a shift. So they don't change equilibrium concentrations or the equilibrium constant. So keep in mind, you need to be aware of how all of these stresses are going to cause an equilibrium to shift, and if they change the equilibrium constant or not. So again, the stresses that we went over was the addition of catalysts or inert gases, volume or pressure changes, which again is only going to affect gases. We also went over energy and temperature changes. So this is the one that is going to affect the equilibrium constant. And we also went over concentration changes and how those affect equilibriums, or how they cause equilibriums to shift. So as a summary here, let's talk about our stresses that we've gone over. Actually, before we do that, let's talk about inert gases and where you can find them, just so that if you see it in a question, you know what they're talking about here. So inert gases, if you look at your periodic table, your noble gases or your inert gases, they are all the gases in group 18. So that's going to be helium, neon, argon, krypton, xenon, radon. It's all of those group 18 gases. Those are called noble gases or inert gases. Okay, so if a question says, oh, neon is added to this equilibrium, how is it going to cause the equilibrium to shift? Well, since neon is a noble gas, it's not going to cause any shifts in the equilibrium. So xenon, neon, argon, so on and so forth. These are just a couple of examples, but they're all the gases in group 18. Okay, now let's move on to our summary. So for concentration and temperature changes, those are going to be the ones where if you add to the system at equilibrium, the equilibrium will shift away. Whereas you take away, equilibrium shifts towards whatever you took away. Okay, and that's just because when you take away something, the equilibrium is trying to replace what it lost. And remember, temperature changes, and it's specifically only temperature changes, those will affect your value for your equilibrium constant. But nothing else does. For pressure and volume changes, remember those are only going to affect equilibriums that have gases in them. And it's based off of Boyle's law. Okay, so Boyle's law states that there's an inversely proportional relationship between pressure and volume. Okay, so when pressure increases, volume decreases. When pressure decreases, volume increases. So with pressure and volume changes, I find it's more useful to focus on what's happening with volume, just because as we wrote in our notes, it makes a little bit more sense if you focus on what's happening with volume, because you can either figure out if there's more or less space for your moles of gas. So if you increase volume, pressure decreases. So your equilibrium is going to shift towards side with more moles. If you decrease volume, that's going to increase pressure. Your equilibrium is going to shift towards the side with less moles because there's less space. Okay, and then the last one that we talked about was catalysts and inert gases. So remember, these do not affect equilibrium at all. Catalysts do help the system to reach equilibrium faster, but if you throw in a catalyst at a system already at equilibrium, it's not going to change anything. Same with inert gases. If you throw in an inert gas at a system or in a system that's already at equilibrium, it's not going to change anything. So there will be no shifts that happen when you throw in a catalyst or an inert gas into a system already at equilibrium. So keep in mind, you need to be aware and be able to apply your knowledge of all of these stresses. So changes in concentration and temperature, changes in pressure and volume, and catalysts and inert gases. And you need to be able to say which way the equilibrium is going to shift, whether products or reactants are favored, what's happening to the concentrations of reactants and products, whether your equilibrium constant changes at all. You need to know all of that and be able to apply your knowledge with that. So remember, the only thing that can actually change your equilibrium constant is temperature. When concentrations are changed, equilibrium is restored through chemical shifts. So that's when you shift, your equilibrium shifts to the left or to the right. Okay, another way to say that is your equilibrium shifts to the reactant or the product side. Altering pressure may seem to alter equilibrium, but it doesn't. So what that means is when you change pressure or volume, you do not get a new value for your equilibrium constant. Okay, so this is just due to partial pressures, which is something that is covered in university. Okay, so we have a couple of equilibriums where I'm going to be showing some videos of them. So the first one is cobalt-2 chloride in equilibrium with cobalt hexahydrate. So the cobalt-2 chloride, that one is blue, or that is a substance that is blue. Whereas the cobalt hexahydrate, that is pink. All right, so let's look at these proposed stresses being added to this equilibrium. We'll make our prediction, and then what we will do is we'll watch the video and record our initial and final observations. All right, so the first stress that's applied is heating the system by placing it in hot water. Okay, so if we're placing the system in hot water, you're going to want to pay attention to your energy term and where is it. Okay, so look at this equilibrium and make your prediction for what would happen if you heated the system. So you're increasing the amount of energy. Now with the second stress, we're cooling the system. So that means we're removing energy from the system. So give your prediction a shot. Pause the video to give yourself a couple of seconds to think about this. And I'll write my answer in a second. All right, so for adding heat, that means we're increasing the amount of energy. So as you add energy, system shifts away. So the prediction would be that your equilibrium would shift to the left side. And what that would cause is, since we're shifting to the left-hand side, we would expect the solution to turn blue because more cobalt 2 chloride is being produced. So solution, I'm abbreviating it, turns blue. Now, when we cool the system, that means we are removing energy. So we're taking away energy, so equilibrium shifts towards. So we would expect the equilibrium to shift to the right-hand side. So we would expect the solution to turn pink because more cobalt hexahydrate is being produced. So we'll fill in this column once we watch the videos, but I want to move on to these other changes and what we can expect. Okay, so the first stress being applied is increasing the amount of chloride ions by adding, you could add sodium chloride. In the video, he adds hydrochloric acid, but it's the same result because hydrochloric acid has chloride ions, so it's still increasing the amount of chloride ions. Okay. So take a moment to figure out your prediction. So that means which side is this equilibrium going to shift to, either to the right side or the left side, and what color is that going to cause the solution to turn, either pink or blue? Now for the second stress, we're decreasing chloride ions by adding silver nitrate. So what this does, silver nitrate, when you put it in water, it's soluble in water. So an ionic compound that's soluble in water, it dissociates, and this is going to dissociate into silver ions and nitrate ions. And what happens, or how this causes a decrease in chloride ions, is that since this has a negative charge, it's going to react with our metal because it has a positive charge, and opposite charges are attracted to each other. So adding silver nitrate decreases the amount of chloride ions because the chloride ions in this equilibrium react with the silver ions to produce a precipitate or a solid called silver chloride. Okay. However, another way that you can decrease the concentration of chloride ions, and what he does in the video is he adds water, which dilutes the concentration of the chloride ions. But both do the same thing. So take a moment to figure out how decreasing the amount of chloride ions is going to cause this equilibrium to shift. So figure out, is it going to shift to the left or the right, and what color is the solution going to turn? So take a moment, pause the video, figure it out. So for the first one, increasing chloride ions. So if you increase the chloride ions, or if you add chloride ions, the equilibrium will shift away. So I would say shifts to the left. So that means the solution is going to turn blue. Why does it turn blue? It's because the reverse reaction is being favored, so we produce more cobalt-2 chloride. All right, now if we decrease the amount of chloride ions, so if we take away chloride ions, equilibrium shifts towards. So we're going to shift to the right, and solution will turn pink, because when we shift to the right, we produce more cobalt-2 hexahydrate. All right, so now that we have all our predictions in place, now we can watch the video and see if we were correct.
Now, on my left, I've got a chemical called, well, it's it's cobalt chloride, but it's dissolved in water. And cobalt chloride in water produces a pink solution due to a cobalt ion which has 6 water molecules bonded to it. You don't need to know that formula at GCSE. At A2 you do, but that's another story. Meanwhile, on the right hand side, we have a beaker full of cobalt chloride complex. It's a nice rich blue colour. In the middle, a purple colour, we've got an equilibrium of the 2 different chemicals mixed together. So we've got some pink and some blue, and just like when you used to mix paints when you were younger, we've got a nice purple colour. Now, let me illustrate Le Chatelier's principle.
All right, so we're going to take a brief little pause here. So as you can see with what he just said, initially, or our initial observations of this center solution, which is showing our system at equilibrium, okay, our initial observations is that the solution is purple. And we're going to write this for everything here. All right, so one thing to watch out for is he's written this equilibrium. He's just written it backwards to how it is in your notes. So just watch out for that, okay? But regardless of that, we will still get the same answers even though our reaction or our equilibrium is written out backwards to his.
I've got some hydrochloric acid, and I'm going to put a few drops of that into my beaker in the middle that's at equilibrium.
So just as a heads up, because he's adding hydrochloric acid, the stress that he's applying is this one. So he's adding chloride ions right now.
Hydrochloric acid, being an acid's got H plus ions, and being hydrochloric acid has chloride ions as well. And this being concentrated hydrochloric acid, we're adding a large number of chloride ions. And watch what happens. You see the solution goes blue. If I stir it round, it's not fully blue, but it's gone a darker purple, a bluer purple. And if I keep adding hydrochloric acid, you can see a very intense blue colour there. Eventually, we will get to a complete blue. We're not quite there yet. We've still got some water present. So we've got the pink chemical and the blue chemical. They're still in equilibrium now, but there's more of the blue, less the pink. Because we added more chloride ions. It says in Le Chatelier's principle, when a system in equilibrium is subjected to a change, the equilibrium will shift to minimize the change. We added lots of chloride ions, so the equilibrium shifts this way, towards the blue end, to get rid of some of the extra chloride ions we added. Those chloride ions we add, some of them will react with the pink to make more blue. Now, we can reverse.
Okay, so how we can update our notes here is we can record our final observations here. So final, after adding the chloride ions, we can say that the solution turned blue. Okay, so for us, because of how our equilibrium is written, that means that it shifted to the left. Okay. So the next stress he's going to apply is the one where we decrease chloride ions, and he's going to do that by adding water. So make sure to watch out for what your final observations will be for this next one.
Reverse that reaction because we could add some water. Now, if I just get a beaker of water, if I add a bit of water back, so we're adding something now to the right hand side, we're increasing the amount of water in our system. Just pour in some water, and straight away you could see pink, and didn't take much water. We've already gone back towards the sort of purple colour we started off with, and we're very close to the pink. So that's one thing we can do. If we add more of the chemical on one side, on the left, more chloride ions, it shifts towards the bluer side, it goes to the right. If we add more water, it goes to the left. And that is Le Chatelier's principle in action.
Okay, so just as a reminder, when he added the water, the solution turned pink.
Pink, and didn't take much water.
Okay, so what we're going to do for our observations is we're going to write that in. Okay, and again, because of how our equilibrium is written out, yes, this would be shifting to the right. Okay, he only said that it shifted to the left just because he has his equilibrium written out just backwards to ours, but that's okay. Okay, so if he had added the silver nitrate, like how our notes were saying, just as a reminder, what would be produced is the silver ions would react with the chloride and it would produce silver chloride, which is a precipitate. It's insoluble in water. So that's what this question's asking about, just what substance would be produced. So we'll just write that in, even though it didn't happen in the video. Okay. So if silver nitrate was added, silver chloride, solid because it's insoluble in water, would have been produced. Oh, sorry, I had said aluminum chloride. That should be silver chloride there. Okay, and what this does, what the production of silver chloride does, is it removes the free chloride ions because they're trapped in the precipitate. Okay, so the next stresses he's going to apply are these two where he heats and cools the system. So make sure to record your final observations. So we'll just record the color changes here.
Water, we've already gone back towards the sort of purple colour we started off with, and we're very close to the pink. So that's one thing we can do. If we add more of the chemical on one side, on the left, more chloride ions, it shifts towards the thing to notice with Le Chatelier's principle, and that's the effect of temperature. Now, if I just move my blue chloride substance and my pink water substance out of the way a minute, I'm going to take my mixture here and I'm going to put it in 3 separate boiling tubes. And I want about the same amount in each. Try and do a fair test. And I'll show you in a second that they look pretty much the same. It doesn't have to be exactly the same. There we go. Similar amounts of 3 purple solutions. And I'm going to put one of my solutions in ice. So in it goes. I'm going to leave one of my solutions at room temperature, and in my third solution is going to go in water that I boiled a couple of minutes ago from the kettle. Let's see if we can spot any difference. So we'll give them a few seconds to shift. Remember what we've done. According to Le Chatelier's principle, if we subject an equilibrium to a change, the equilibrium will shift to minimize that change. So if I heat something up, it will go in the direction that tries to cool it down, and that is the endothermic direction. If I cool it down, it will go in the direction that tries to warm it up, the exothermic direction. So Le Chatelier's principle is a bit like Sod's law. If you try to do one thing, the chemicals will try and do the opposite. I try and heat it up, the chemicals will go endothermic, they'll try and cool down. If I cool it down, they'll try and go exothermic, they'll try and get hotter. Okay, they've been in the beakers for long enough now, and if I take them out, okay, the difference between the one on the left and the middle isn't that great, but the one on the right you can see has gone very blue. So, when I make the chemical very, very hot, that was the boiling water, the water out of the kettle, it goes in the blue direction. When I make the water very, very cold, it tries to go back in the pink direction. So this tells us something important about our reaction.
Okay, so now let's record our observations here. So when he heated up the solution in the test tube, it turned blue. And when he cooled the solution down, or when he cooled the solution in the test tube down, it turned pink. For this next equilibrium, we have dinitrogen tetroxide in equilibrium with nitrogen dioxide. What we're going to do is we're going to watch a video that cools this equilibrium down and heats it up, and we're going to record what colors it changes. Okay, and we're going to record which way the equilibrium shifts based off of what color it changes. But please keep in mind that how the video has the equilibrium shifted or the equilibrium written out is going to be backwards to how we've written it out. Okay, so just keep that in mind. We are going to base our answers on how it's written, how the equilibrium is written out in the notes, but just be aware of that.
The conversion of red-brown NO2 to colorless N2O4 is an exothermic reaction. We're going to use Le Chatelier's principle to predict the shift of the reaction with respect to temperature and also the color. Because this reaction is exothermic, heat is a product. Therefore, adding more heat to the reaction will shift it towards the red-brown reactants, the NO2. Placing the other tube in cold water is the same as removing heat from the reaction, so removing a product. That will result in the conversion of NO2 to the colorless N2O4.
Okay, so let's back this video up a little bit so that we can see those colors. So remember, the test tube on the left is being put in hot water, whereas on the right it's being put in cold water. So when cooled, the tube turns like a lighter brown. So it turns more colorless, but it doesn't ever reach colorless there just because she didn't leave it for very long. But we are going to say that it turned a lighter brown. So that means it's moving towards the colorless dinitrogen tetroxide. So that means that the equilibrium shifted to what side? Left or right? Take a moment to write it down for yourself and pause the video. So when the tube got cooled down, we produced more dinitrogen tetroxide, which resulted in the tube becoming a lighter brown. So that means it shifted to the left, or you could also say to the reactant side. Now, when the tube was heated up, again, looking at this picture, the heated up tube is on the left-hand side. Notice how it turned a darker brown. So if it turned a darker brown, that means we produced more nitrogen dioxide. So if we ended up producing more nitrogen dioxide, which side does that mean the equilibrium shifted to when it was heated up? Take a moment, write down your prediction. So when the tube became a darker brown, that means we produced more nitrogen dioxide, so it means the equilibrium shifted to the right. Okay, so this means the above equilibrium, is it endo or is it exothermic? Okay, so based off of our observations, okay, when it was cooled, the reaction shifted this way. So when we took away, the equilibrium shifted towards the left-hand side. So remember, for our stresses, when you take away, the equilibrium shifts towards what you took away. So this indicates that the energy term is a reactant. Okay. Alternatively, you could look at the evidence that we collected for when the tube was heated. Right? When heated, the tube got a darker brown, so it shifted to the right. Remember, when you add, the equilibrium shifts away from what you added. So when we increase the amount of energy, it makes more sense for energy to be a reactant, because when you heated it up, it shifted to the product side. So because energy is a reactant, that means it is an endothermic reaction. So what they mean by this, just because we can read reactions forward and backwards, I'm going to specify by saying the forward reaction is the endothermic reaction.